So yeah, before continue with the with the relaxed memory consistency model, let's say just a small comment about the basic synchronization technique or knowledge that we need to understand the next of the chapter. So communications from shared memory space need synchronization between processors. We know that because we are programming in parallel and we are programming in OpenMP, and if we don't use synchronization mechanisms, our program will not work as expected. We need synchronization, and we need it because we are not programming on a multiprocessor with sequential consistency. We are programming in a multiprocessor that relax one of the restrictions. So we must take care about the data dependency. If I need, or I want to give access to only one of the processor, I need to create a mutual exclusion that ensures that only one process can be accessing the shared address at a given time. But I can also, or I may also need collective communication, so I can coordinate multiple accesses to the same same shared variable. I will give you more detail in the synchronization part, but that is enough for now. We need synchronization because we are going to relax some of the restriction, and then and because we are not programming in an architecture with a sequential consistency model. So if there are some data dependency that I need to take care, I need the synchronization. So with respect to the program order, I can classify the relaxing model according to the read and write ordering they relax. We are going to define X before Y. That means that operation X must be complete before operation Y. So I can relax Y right before read ordering. So in this case, Y must complete before subsequent read. That is what I'm relaxing, I mean. I can also relax Y after Y. So Y must complete before subsequent Y can be relaxed and reordered. And I can relax all the four ordering. Y before read, Y before write, read before read, and read before write. As we say, sequential consistency relax nothing. That is the reason why it's the more restrictive. That is the reason why the program will work if I execute them in a sequential consistency model over a sequential consistency model. The first one is known as total storage order or processor consistency model, where write followed by a read to different locations can be reordered. So we now allow the read to be reordered with respect to previous write from the same processor. This model retains ordering among writes. That is still a restriction. Many programs that operate under sequential consistency operate also under this model. This helps us write latency in the write operation. There are many differences between these two variants, where total storage order is more restrictive than processor consistency. In total storage order, I allow a read to return the value of its own processor write. So even before the write is serialized with respect to other write to the same location. However, a read is not allowed to return the value of another processor write until it is made visible to all other processors. On the other hand, processor consistency, a read can return the value of any write before the write is serialized or made visible to other processors. So the main difference here is that in the total storage order, this program that we saw that we saw before, work expected if it is executed in a total storage order over a total storage order memory consistency model, because the read is not allowed to return the value of another processor write. So this read here, when processor 2 read the value A, it's not allowed to start until this write is finished because it's in different processor. So I can be safe, so don't worry because this is going to work as expected. However, if I execute this in a hardware with the memory consistency, with the processor consistency memory model, this read can be done before this write because a read can return the value of a write of any write before the write is serialized or made visible to other processors. So in this case, I can return an old value here respect to the write that was performed in a different processor. And this ends with inconsistent result, for example, b equal 1 and register 1 equal 0. So as I have started to relax some of the ordering, now I need safety net that are explicit fence instruction provided to override program order relaxation that are available in the different instruction sets. So this way I ensure sequential consistency with read modified write operation to provide the illusion of program order and atomicity. Disadvantages are that the system may not implement the general read modified write for replace any read or write operation, and replacing a read by a read modified write incurs the extra cost of performing the write. This means that I introduce in an overhead because even if I want to make a read, it will be a read modified write operation, so I end with writing the main memory. We can implement this, or this is implemented by processors that use the first in first out write buffers. So this improves performance at the hardware level by effectively hiding the latency of write operation, and the read in case of need can be done directly from the buffer in total storage order and processor consistency model. Must check, however, that no read after write has occurred, so it's not so beneficial for compiler optimization still. The ability to only reorder a write with respect to a following read is not sufficiently flexible. So we can then relax also the write following by a write to a different location. So now a write to different location from the same processor can be pipeline or overlap and are allowed to reach memory or other cache copies out of program order. This is known as partial storage order model, where a processor can read the value of its own write early through the write buffer, for example, but not from the write of another processor before the write is visible to all other processors. This is illustrated in this example that allows not sequentially consistent result because if processor 0 write relax the write before write, this second instruction can be executed or this write can be ended before A is equal 1, so processor 1 can leave the loop and use A with a null value. Using A, suppose it is previously initialized to 0. So this work, just a recall, we are in multiprocessor, so this doesn't work if we are in a partial storage order memory consistency model, but nothing is wrong if we execute this program in a single processor. Because in that case, the hardware and software is aware about the data dependencies. So what can we do? Add safety net in the point that I want to ensure the ordering of my program. In this case, between the two write, ensure sequentially consistent result in the example. Again, this is trouble for the compiler optimization. Finally, I can relax all the for ordering, and in this case, I find a various model depending on the implementation. For example, with ordering, release consistency, this is the one available in RISC-V IRM consistency architecture. Also, relaxing memory order, digital alpha, another IBM PowerPC model. We are going only to discuss the first two with ordering and release consistency. Now, a read or a write operation may be reordered with respect to a following read or write to a different location. The order in the accesses is changed as long as there are not conflict between the access whose order will be altered. On the one hand, in order to understand the weak ordering model, now the order between accesses only, I must ensure the order only between accesses at the, order between accesses only at the code synchronization point. So now I need to classify operation not only in write and read at the beginning, but also in synchronization. So now I have three types of operation. Well, actually two types, data operation and synchronization operation. So we, as the programmer, must identify at least one of the operations as a synchronization, and it is based on the idea that reordering data region between synchronization operation does not typically affect the correctness of a program. This is what we are actually, I think, doing when programming OpenMP. We introduce synchronization point, and we don't worry about what happened in between. We know that the program must be correct before and after the synchronization point. So no operational issue until the previous synchronization operator is complete. We have now the new relationship that are write and read before synchronization. So memory access operation before the synchronization must be complete in program order, and also a relationship synchronization before read and write and read. Memory accuracy operation after synchronization must wait for the synchronization end. Illustrated in this figure, I have three processors with two synchronization points, and in a weak ordering model, I know that these three operations will be executed before the synchronization point, but in any order, I don't mind. After the synchronization point, the next four instructions will be executed again at any order, of course the same order for all the CPU, for all the processor, will be executed before reach this synchronization point, and finally the four last operation will be executed after the synchronization point. So the synchronization operations are sequentially consistent. When several processors emit a synchronization operation, some order is chosen, whatever, but everyone sees the same order. Ensure that write always appear atomic to the programmer. So the safety net is required for write atomicity. At the end of the synchronization, write always appear atomic between synchronization, and must finish all pending memory operations and stop new ones until the current ones are finished. It is not so efficient. And this is not so efficient, so we can do it even better if we move to a release consistency model. This is the one consistency model that we're going to see in this class. In this case, memory operations are classified in data as before, but now in two different synchronization operations, acquire and release. Acquire operation is a read memory operation that is performed to gain access to a set of shared location, and release is a write operation that is performed to grant permission for accessing a set of shared location. So when a process leaves a critical section, it is it is not necessary to have all the operations carried out immediately. I don't need to finish. I don't need to stop at the end of the synchronization. I can keep keep on executing instruction because I only need to make sure that they end before other processor enter that critical section. So I need to finish them before the next processor try to acquire or try to emit and acquire synchronization operation. This gives us a new relationship that is acquisition must be acquisition before write and read, keep program order between acquisition and any subsequent operation, and write and read before release, keep program order between any memory access operation up to subsequent release. So a read or a write that follow the release, no need to wait for the release to complete. Acquire normally read a synchronization variable and automatically update it, and the release usually just write the value to specify that a critical section is finished. If the net acquisition occurs sufficiently long after the most recent release, we don't need to wait. The program can enter the critical section, and we don't delay the execution of instructions so often. By relaxing this ordering, this forward ordering, the processor obtains significant performance advantages, which are the reason why RISC-V, ARM, as well as C++ and C language, also a slightly variant of OpenMP interface, we choose release consistency as the model. To sum up the difference between weak ordering and release consistency, this figure illustrates the workflow of the acquire and release and how I must wait for the operation in between acquire and release in order to continue the execution of the program. In this order: 1, acquire; 2, operation of over data; 3, release; more operation, then acquire again, more operation, and release again. However, if I move to a release consistency, for example, this block that is the 4, that is here, can be executed after or in parallel with block 2 and any interleave, because I need only ensure that at point 5, as here, this instruction that are in between an acquire and release, so this instruction finishes before I acquire the, so I emit the acquired synchronization in this point. This is a summary of the different memory consistency model that we see in this video. From sequential consistency, that is most resistive, until release consistency, that is the more relaxed. These are the ordering that they retain, and these are the synchronization relationship that we must guarantee in order to execute the program correctly. So keep in mind that now we are in a parallel and a multiprocessor with the shared memory architecture. So systems currently do not guarantee, these systems currently do not guarantee sequential consistency, and we cannot assume an order between synchronization points, only before and after the synchronization point. Assume the order just before and after the synchronization point, and use synchronization primitive that ensure the necessary ordering for the corresponding consistency model. Okay, that's all for this video. I will now prepare the next one for the synchronization.